Okay, so I will show you these slides to try to make, I hope, an introduction to the second step, that is what we're doing with Victor. Okay, so the case of the moon. So the first part is to consider a manifold, a surface in our case, with constant metric G. And the problem is how to extend the definition of gravity to a general manifold, the one, that we are so familiar in our Euclidean world. And I will show you that by our choice, we use the Hodge decomposition theorem, that basically nothing is than Maxwell law adapted to gravity. I hope at the end this will result clear. So first of all, just a comment that, like when we have observation in general, we want to, we have two different approaches, theoretical modeling and empirical modeling, and both, they will merge to bring to some mathematical models. And in general, this is much of interest, both from mathematical model point of view. And when we talk about, in particular, when we talk about theoretical modeling, what we need is to set up what are the axioms, meaning the working hypothesis or postulate of our theoretical model, the basis, the over which we built our theory. And so then the choice that we make eventually are confirmed, one hope, by experiment or further observation. So this is the first point. So we have example of this axiomatic theory. We know very well the one of geometry, Euclidean or no Euclidean geometry, and we are very familiar with the choice of assume or not the fifth postulate that make possible to create new extension of new kind of geometry. Felix Line definition of what it is a geometry. And so, for example, we're very familiar with the fact that spherical geometry is the Earth, so the extension of the notion of geodesic, the big circle, and this big circle, eventually they all cross the meridian, the one that comes from the meridian, they all cross to the poles, even if in principle they're all perpendicular to the equatorial circle. Now, we have another example of axiomatic theory, that is the Newtonian law of mechanics. We have the first, the second, and the third. Those are axioms of mechanics. They were eventually tested by experiment. And then one can ask if actually these axioms, they're actually of our Euclidean word, they're actually universal and they're valid in all geometry. So now we come to gravity. And so what will be the general definition of gravity? How to define gravity? And eventually what we saw also from our previous work, the gravity and incompressible fluid are related. I will not talk this in this first part, but eventually how to define incompressible fluids. This will be another question. So how to define gravity? We're familiar with gravity in our Euclidean three-dimensional world, and we are familiar that we have Newton's law of gravity. The force are inversely proportional to the square of the distance, and also the fact that those are attractive central force, meaning like not rotationally, they don't have a rotational component. And also we have Kepler law. So we're so familiar that these three properties, let's say, they are all valid at the same time. But actually, are those three universal? Meaning, are those still valid in all geometry? Are those are all of the three are axiom of gravity in a more general sense. And actually, already in Arnold's book, state and make a comment between the lines of Arnold's book of classical mechanics that actually already in the plane view as R2 and not the plane forced by conservation of angular momentum, really a b-dimensional gravity, already Kepler law are not more valid, and this will comment further on. So really the three, already if we go to the plane, the three are not compatible and we have to make a choice. So some people choose to use Kepler law as a definition and some other people choose to impose as a view of our surface as embedded in our tree. They choose to project, to force one where our potential, to the surface has embedded in our tree. We choose the attractive central force as our definition. And this is for us as a natural choice because this actually follows Maxwell, what Maxwell has done for electromagnetism. And so this will be our definition. And so following Maxwell, so 19th century gravity, if we have a test particle, and we can imagine that we have a source mass, this M, big M, and then we have a sphere around it. So we have here, imagine is a three-dimensional sphere, and we have all a dust particle that our satellite or test particle at a distance r from the sphere. And so we want to measure what is the force acting on each of these particles. And so we can imagine like the acceleration field at this point. And so the acceleration field following Maxwell would say, okay, it's central force, so D is irrotational. But then at the same time, there is a second equation that is not divergence free, because actually this sphere will actually be attracted by the central mass, would reduce the volume with the time. So this reduction of volume is expressed by this divergence being negative. And what is in here S is the source of the field, that in this case is this, an example is the central mass, okay? So those are the field equation, okay? These are our field equation. And actually there is an extra condition that also we'll talk in some other parts, meaning that we want that, especially in R3 and R2, we want that the potential that we derive far from the source will go down to 0 at infinity. Okay, so this is the extra condition that is hidden in the theory. But anyway, what we, from the first equation, the fact that is irrotational, we can make use of an auxiliary function so far, phi, and we can rewrite, so we can rewrite A as minus grad of phi, minus the gradient of this phi. And in fact, if we substitute this into this equation, this is automatically satisfied. So in this sense, we can make use of this auxiliary function. And then once we have this, we rewrite A as this, we can we substitute in the second equation, and we can derive the equation for the gravitational potential of the test particle. So now, what is the advantage of this approach? Then now we gain an equation to compute what is the gravitational potential, okay? So this is a gravitational potential. And so given a manifold M, in our case a surface, with the metric G, we correspond to we can compute what is the corresponding Laplace-Beltrame operator, and this equation, for a given S, a given source field, we can actually derive our gravitational potential. And so if we do this, for example, in R3, and we can just put here a point like a particle, source field, this solution of this equation give us this gravitational potential that eventually brings to the known force that we know. So we have derived Newton's law from Maxwell equation. Okay, so this I think is very nice, and actually this equation allows us to derive the potential for very general surfaces. So this is the nice news. And in fact, if we take surfaces that are not compact, here we have more general potential, even the one for the plane, that is log of R, and in this case the force for the planar force is, you see, that is different from the R3 force. So it is the intrinsic, in the intrinsic geometry. And just as a remark, I think that after done electromagnetism, gravity should be reviewed. So we have, this is actually very similar to electrostatic. The only difference is the sign, because we know that in electrostatic, two equal charges are repelling, and here they are attracting. So the difference is in this sign, okay, this sign. And of course, classically, we also will have conservation of matter that is expressed by a third equation. Now, the other remark is that, okay, what we done actually, we have extended to arrive to that equation, a general equation for a general surface. We have extended this notion of attractive central force for a general Riemannian manifold by using the Hodge decomposition theorem. So this is what is hidden behind that general formula. And so what is the Hodge decomposition theorem? So we have two versions of this, and it's funny because each community doesn't know the existence of the other. So we have a definition of Hodge decomposition theorem for vector fields, the Helmholtz-Hodge decomposition theorem. And this actually is very well known in as a fundamental theorem of vector calculus. And this is actually a theorem that allowed us to, as we saw, to derive the Newton potential, as we know, for R3. Here is missing a 3 again. But also there is another version of the same theorem for differential forms. So here is the version for vector fields. They say basically that each vector field can be decomposed into components. A component that has a irrotational, but is not divergence-free. A second component is divergence-free, but is rotation. And then there is the harmonic component. And as you can see, this is valid for whatever vector field. So if it's velocity field, or if it's an acceleration field, and if it's an acceleration field, in our case, we make use of this decomposition as we're interested in this class of fields. When we do incompressible fluid dynamics, we are interested in this. We talk about decomposition for the velocity field, and we're looking for incompressible fluid. That would be this. And now the same theorem for compact surfaces where we can, map our velocity field. We can associate it through the metric in one form field, and everything can be formulated geometrically through a Hodge operator, and this is how we rewrite the Laplace-Beltrami in a total general independent of the choice of coordinate forms. So the Hodge decomposition theorem also has a similar in differential forms decomposition, just where those are differential forms, and this once more is the harmonic part. So here we see that there is an ambiguity about this harmonic part, because actually it's a not unique decomposition, because we can always add this third component to one of these other two, to 2 or 1. So this is a kind of, we want to reduce this ambiguity about the harmonic part, and this why is needed in general an extra condition to reduce the ambiguity of this third part. And this, when we say is the potential is defined up to a constant, is that because in R3 and R2 we have said that we wanted the field goes to 0 at infinity, far from sources. So okay, so now to conclude, there is a third remark, is that for mechanical system we also would need a kinetic energy, so for our test particle. So this is we were very happy to find phi, the potential energy for our test particle, but now we want to find k, the kinetic energy. But actually this is, we have it for free, because we are considering a Riemannian manifold. So there is a metric defined on the tangent for as an inner product for the tangent vector. And actually, since we need an inner product for the momentum in the cotangent space, this is given for free by the inverse of the metric. And so we have our kinetic energy for our Hamiltonian formulas already well defined. Okay, thank you. So this is just the first part.